In this video, I'm going to give a very brief introduction of equilibrium as a concept, and in subsequent videos, we will actually work with numbers and look at it more quantitatively. So, the main concept of equilibrium is that there is a set balance between reactants and products of certain equations, and that balance is dependent on temperature. And here in this example, we've got an N2O4 going to NO2, and at really cold temperatures, this N2O4 is solid and it has no color, because N2O4 is colorless. And so since it's frozen solid, there's nothing really to see. With NO2, though, you start to see some reddish brown color showing up, and that this has happened because this is starting to melt and this is dissociating into NO2. So this is a decomposition reaction. This is breaking down to form this. And then at the right, we see there's an equilibrium between the two. There's no further color change. So the reason why the color is changing here is because it's currently N2O4 is the predominant species, and then the NO2 hasn't fully reached its potential concentration yet. So there is this point at which the reactions will approach each other in rate. And once that happens, then there's no noticeable change. So let's take a look in more detail at this idea. So here we have three reaction systems, and we're looking at them at different times. And so in this one, we've got this time 0, and you see you just have little blue circles instead of the purple ovals. So the blue circles is our reactant and the purple ovals is our product. And we have three different reaction systems. And you could imagine that this is at, say, 3 different temperatures. So while the reaction may look the same, there's going to be a different endpoint because the temperature is different. And so here's our time 0. We're starting off our reaction and we've only got reactant. We don't have any product yet. And then over time, product appears. So what we see here is that this system, it looks like it has achieved equilibrium at time 2, where we have 4 purple ovals and we still have 4 purple ovals over here. But you'll notice that they're not in the same exact place. And that's because what's happening is one of these blue dots might be changing into a purple oval, and then another purple oval is going to form. So for example, this at time 2 and time 3, they're at equilibrium, but this one has turned back into a blue circle. And this one up here may have turned into a purple oval. So you keep the same total number, but the reactions are still occurring. So let's look at reaction system 2. We can see that we have product or reactant only here, and then more and more product forming. And we see we have 2, we have 4, and then we've got even more. So we can't actually say for sure if this reaction has reached equilibrium yet, because we have nothing to compare it to. This might very well be equilibrium, but we would have to look at another time point to know for sure. If there was no change at a later time point, then this would be at equilibrium now. For reaction system 3, we see that between time 2 and time 3, there's no real change. So again, time 2 is where this reaches equilibrium. So here's just another example where you can see the same ideas of the different reaction systems. And so what we're talking about when we say a reaction has reached equilibrium is that the equilibrium concentrations of product and reactants have been met and the rates are the same. So let's explore what we mean by this a little more deeply. So in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So you could imagine over time, you've got your concentration, and we're starting off with 0 product and only reactant. So over time, the concentration of the reactants decrease and the concentration of the products increase until they flatten out and there's no more change. So there's no more net change. That doesn't mean that individual reactions are not occurring, because they are, but there's no net noticeable change. And the ratio of those concentrations, the ratio of product over reactant, is going to be constant at a given temperature. That is what an equilibrium constant is. So you'll want to watch that video for an explanation of what an equilibrium constant is and how to write equilibrium expressions. But for now, I just want you all to be very comfortable with the idea that at equilibrium, reactions are still happening. They're just happening at the same rate in forward and reverse. So for example, your body is in homeostasis. You've probably heard that term before. And we as mammals are warm-blooded. We can generate our own heat. So we maintain a body temperature of about 37 degrees Celsius. Okay? So we maintain that body temperature, but we still have heat leaving, energy leaving our body, and we're absorbing energy from our environment. So it's a dynamic equilibrium. We are not in equilibrium with our environment, because if we were, we would be dead. We would be not exchanging any energy or matter with our environment. But we are, and yet we still maintain the same size, roughly, and we maintain the same temperature, unless there's an illness. So when equilibrium has been reached, we get to see that the reaction rates are equal. So how do we know we've gotten to equilibrium? Well, it's that ratio of product over reactant at any given temperature is a special value called the equilibrium constant. And in our next video, we will discuss the equilibrium constant expression and how to calculate it.